How many muscles do we have in the body? Over 600. Okay? Some of these muscles, very deep, but their job, help us maintain posture, help us walk, help us carry out a lot of activities we don't really think about consciously. Do any of you remember learning how to walk? Mm-mm. Have you ever watched a baby learn how to walk? Kind of, you know, bless their hearts, bunch of falling down, okay? I'm convinced that's why diapers are so thick, okay? But this is one of the things that happens, and because of this, it's termed a pattern generator. Your muscles, when you do an activity repetitively, the muscles actually learn that, and you don't really have to think about it. It stays on like a reverberating circuit, one that's going to continuously go round and round. Reflexes. What comes to mind when you hear the term reflex?
Reaction.
Hold on, remember, y'all don't ever talk each other.
Yeah,
Nate?
I apologize. Like when you go to the doctor and they do the little, they hit you with the knee.
Hit you with the knee. Yeah, you gotta love that one. Nate?
That's Monty.
Monty.
Sorry. I'm sorry. What I say, reaction?
What kinds of reactions? Jerk reaction. Okay, like if we're back at the doctor, we think about the one they do to the knee. Sometimes they might do one to the elbow, one to the arm. They got all these things that will do. We're going to find that reflexes, because with the ones we mentioned, they're pretty much due to skeletal muscle. And because of that, they're ones that we tend to know a whole lot about. But did you know that your organs have reflexes? Yeah. So it gets really interesting. Reflexes, they're vital to us. Organ-wise, they help keep us alive. Reflexes with our skeletal muscle, they help us with our posture, maintaining that upright posture. They help with motor coordination, like if you're trying to learn a new technique of something. And then they're protective, like pulling away from something hot or painful. When we begin to look at this anatomy of the spinal cord, they term it a cylinder because that's what it looks like. It looks like a cylinder along those vertebrae. It arises at the area of the brainstem, exits through the foramen magnum, passes through the vertebral canal. Now, this is something that people, first time they hear it, they're kind of like, do what? It goes roughly to L1, meaning, if you look at this right here, this is representing our spinal cord. And at roughly L1, we get this huge tapering that takes place. And then it begins to look like all this string that's coming off of it to go the rest of the way. Pretty much what happens. The spinal cord is going to give rise to a spinal nerve. Meaning, as we travel the vertebral column, because of the way that the vertebra articulate, we end up with lots of foramen. And if you remember from the structure, we have some of these lateral foramen, and they allow for a spinal nerve to exit out of every vertebra, between vertebrae. So for every one that you see here, see how they're trying to represent it going around and around, okay? Every one of these is considered a spinal nerve. The area that it's exiting from one vertebra to the next, and then underneath that vertebra, we have segments. So you would, like if we're looking at cervical, thoracic, lumbar, as you go down each one, every one is a segment. So C1, C2, C3, C4, and so forth. And then that spinal nerve exits from it. So that's termed the segment. On the spinal cord, which probably can't view very well from here, but right down through the middle, be sure to check this out when we go on break, okay? Now, this, of course, would be the anterior view of it, okay? But it's also present on the posterior. It looks like this huge line, this huge indentation, which if you remember, that's a fissure, okay? So on each side, it looks like it's divided, sort of, okay? And our understanding, yeah, that makes sense. And so we're going to see on both sides, we have this really prominent line. When you look at graphic representations, this is the representation you're usually viewing. They're showing how it tapers at roughly L1 as an adult, okay? We have areas that they consider enlargements. For example, lumbar, okay? The reason for that is because it's going to serve the lower extremities. Okay, I've got a cervical enlargement for the upper extremities. Now, here's some of the cool stuff that's going to happen when we look at the spinal nerve portion. Okay, so if this is my spinal cord, and then I have segment, 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 that nerve that we see exit, what do you kind of notice this nerve doing once it enters into the vertebra? What does it look like it's doing? Remember, kind of don't overtalk each other. Doing what? Doing what?
Oh, I said bring them out.
Okay, breaking out. Maybe doing a spreading, okay? Those are going to be rootlets, all right? They're going to be important. You're going to find them on both sides, anterior, posterior, okay? There's a reason for that, which we'll get into. Do you see anything else happening with the nerves that are coming into the spinal cord? Do you see these little bulging areas? Okay, those are going to be termed ganglions. All right, so ganglions, all right, they're going to be areas that are going to be important. All right, so the spinal cord, as we continue to look at it, it's going to taper. We're going to end up with what looks like this huge string-like appearance. This is actually termed the cauda equina, equine horses, because it looks like a horse's tail, okay? And what these nerves begin to do, they're going to continue down through L, they're going to move into S, they're going to move into the coccygeal region, and then they're going to be exiting. They're going to exit as very large nerves because they're serving the lower portion of the body. Okay, they are serving this lower portion that has to support all the weight. Not just the weight, but what also gravity pushes down on us. okay? And for every pound you weigh, based on gravity, by the time you get to your ankles, it's a little over 9 pounds of pressure that you're carrying for every pound you weigh. So if you weighed 100 pounds, by the time you get to your ankles, that's 900 pounds that they're having to support. Yeah, based on gravity. That's why there's so much damage to the lower half of the body. If we look at a cross-section at one of the segments, we can see how this spinal cord is very well protected, encased in the bone. We're going to find that it's got the meninges that wrap around it. We can see how the nerves are going to enter. But now, if this is the big spinal nerve entering, looks like it's doing this number right here too. We'll get to that, okay? Right now, we want to focus on the spinal nerve as a whole. If we look at our different segments that we can see, we're going to find that we have gray matter, we have the white matter, we've got the spinal nerve. Remember how I said the rootlets? We're going to have some to the anterior, some to the posterior, because we have to have information go in and response come out. So information going in is by one direction, response out is the other. Okay, we're going to get into that. So that's why we have this where it looks like it, does this number, like it forks, okay? And we have part of it go to anterior, part of it go to the posterior. When we look at the gray matter, this would be what we think of as not having myelin. Not necessarily the case. Myelin is present. It's just different. All right? And the white matter, it's the one we think of as having the myelin, yes, and a lot of the sheath that's present for that myelin. We're going to see that it has wrappings, these meninges, all right? That's probably familiar, okay? And one of the other things about our nervous system is very well vascularized. It has a huge supply of blood. Why? Don't blurt out. Kind of like, give me a little.
Is it to stay well oxygenated?
Okay, we got to stay well oxygenated, which is which can do what? What can that oxygen help that nerve cell do based on an organelle that it has?
Would it help it move faster?
And what do we need to move faster?
ATP.
Energy. So oxygen. Can you think of anything else that might need to get to that nerve cell from that blood supply?
Would it be sodium?
Ions. Now, the nerve cell has to make sure that when information needs to be passed, that we get that action potential going. But remember, cells, doesn't matter where we're looking at in the body, cells need nutrients. Okay? They're going to need oxygen. They're going to need ions. They're going to need their amino acids. They're going to need their fatty acids. They're going to need all the nutrients that are possible. They're going to need to get rid of waste. Okay? If we make ATP, we produce CO2. We've got to get rid of that. Okay? And if this is a nerve cell, do you happen to remember what the name of the product is that gets made by the nerve cell?
Acetylcholine.
Now, acetylcholine is what we had at that neuromuscular junction.